I'm not sure.
Oh, I guess whatever you think, Bruce or Dave, where you think we're going to start. It's
I think we should go ahead and start and get
Yep.
everything out of the way so that Dr. Tanetta can
Yep.
do her magic.
Okay, let's go.
All
So
right.
tonight's talk is sort of a follow-on or a continuation, if you will, of the talk that we had 2 months ago from Dr. Sarah Seeger along the topic of exoplanets. And it's a real pleasure that tonight we have Dr. Giovanna Tanetti as our speaker. And as I said in the invite, just by way of a brief intro, Giovanna is the head of the group of astrophysics at the University College London. And she's the director of University College London Center for Space Exochemistry Data. She has a long-standing interest in understanding the chemical composition and state of atmospheres in exoplanets.
Okay. Yeah.
And so it's appropriate that she is, in this capacity, the principal investigator for the European Space Agency's Ariel mission, which just got approved last week and will be launched, I believe, Giovanna said, in 2029. And the significance of that, and Dr. Tanetti will touch upon this, is that this mission will help us to understand sort of what exoplanets are made of, understanding their chemistry of their atmospheres, and how these exoplanet atmospheres develop and evolve. So this is pretty critical, obviously, for any study of exoplanetary research. So very briefly, following getting her PhD in theoretical physics from the University of Turin, Giovanna's had a number of different appointments. She's been a NASA Astrobiology Institute Fellow at Caltech. Then she was with the European Space Agency Fellow in Paris. And then she joined University College London in 2007. In addition to having a very, very busy research and teaching schedule, Giovanna regularly speaks on topics of space and planetary science and exoplanets for a number of different audiences on the radio, on webinars. She's been on the BBC quite regularly. So it's really a privilege and an honor that she took this time to speak with us. So tonight, she's going to talk about some work on exoplanets and touch also upon the Ariel mission. So Dr. Tanetti, thank you and welcome.
Thank you so much, Bruce, and thank you all really for attending this talk. It's a great pleasure and a great honor to be with you. Well, tonight, in my case, I guess is during the afternoon in your case. So let's see if I can project my slides. Hopefully everything will be smooth. Can you see them?
Yes.
Yes.
Yes. Okay.
Looks good.
Okay, let me start by saying that if we go back to the 90s, the planets known were 8. 8 because the only one we could count, actually there were 9. 9 because back then we could count the planets in our own solar system, and in the 90s Pluto was still considered a planet. And then since then we have lost Pluto. But at the same time, we have learned that on average, every star in our galaxy on average should host at least 1 planet. And so really planets seems to be ubiquitous in our galaxy. And if we do a brief count, then we're expecting thousands of billions of planets in our galaxy alone, the Milky Way. So unfortunately, we don't know yet these billions of planets, but the number of planets that have been discovered so far is a bit over 4,000. And these are planets orbiting our stars. Out of these 4,000 planets, a little bit more than 3,000 are organized in planetary systems. We already have a moon candidate that still needs to be confirmed. But clearly this field is growing extremely rapidly. And in fact, you can see from this graph where you have the number of exoplanets discovered as a function of time, you can really see there is an exponential growth in terms of discoveries. it's fair to say that truth is stranger than fiction. I think in this area of science, I think this is a true statement. And in particular, we have all sorts of planets out there. And I'm using deliberately some of the images from the Interstellar movie to point to the fact that we have almost science fiction example of planets out there. So for those of you who have seen the movie, there was a planet completely covered by ocean, and ocean world seems to be actually some potentially existing classes of planets. Many of the planets that have been discovered are orbiting very, very close to the star. In some cases, they're doing one orbit in less than 1 Earth day. So at those distances, some of the temperature that we are measuring are over 2000 degrees, so it's extremely hot. And so when planets are so hot, it means that the surface, if there is a rocky surface, then it's molten. And so we call them sometimes lava planet. And again, this picture is taken out of Star Wars. But also, again, going back to Interstellar, you might remember that there was an icy planet. And again, many of the planets discovered so far, in particular with the technique of microlensing, are so far away from the star that we believe they might look like this picture here. And finally, you might remember in Star Wars that there were some planets around 2 stars, orbiting around 2 stars. And these are actually a real example of existing planets. Kepler in particular, the NASA Kepler mission has identified many of these, what we call the circumbinary planets. So again, this is really not science fiction. Kepler, the NASA Kepler mission I just mentioned, has been an incredible success. It was launched in 2009. And additionally to the number of planets that it has discovered, Kepler gave for the first time really a sense of what is the galactic statistics in terms of exoplanets. And what Kepler pointed out is that the most numerous planet out there seems to be planets with sizes in between the size of the Earth and the size of Neptune. And the contrary, planets as big as Neptune or even bigger, like the giant planets in our own solar system, so as big as Jupiter, as big as Saturn, seems to be relatively rare. And this, of course, goes against, in a certain sense, the observational bias, where, of course, the bigger is the planet, the easier it is to detect it. So clearly it means that this statistic is clearly true, because small planets are far more difficult to be discovered compared to the bigger one. And more recently, some refinement of the parameters of the stars that are hosting some Kepler targets pointed out that actually we see a bit of a bimodal in the distribution of planets discovered by Kepler. And in particular, as you can see in this graph, the bimodal has 2 peaks. One peak that is more or less around 1.3 Earth radii, and another peak that, on the contrary, is around more or less 2.4 Earth radii. So we still don't know very well why we're seeing these 2 peaks. And there are a lot of discussion and speculations of the fact that perhaps one peak, the one where we're looking at smaller planets, are more rocky type of planets. And the other peak for that is including basically planets in between the Earth and Neptune, perhaps is including more some ocean planets or some sub-Neptunes. But again, we need to understand much better what's going on. So clearly, this is just the beginning. So fasten seatbelts for the next decades, because what you're seeing here on the top of the timeline, you have all the mission that have been planned or already flying and operating to discover new planets. And in particular, Kepler has retired now after all the successes, but TESS is ongoing and is producing a lot of great discoveries, the NASA TESS mission, and also CHEOPS, which is a small mission launched by ESA, is currently operating. And they're both delivering more and more planets. And then I will mention a little bit what Twinkle is. Plato later on, 2026 or so, again, will deliver even more planets. So clearly, we should expect that in the next decade, we'll have an increasing number of planets really to add to our catalogs, and much more actually to come. So just a few words about NASA TESS. As I said, extremely successful, currently operating, and the mission has been extended. So it's delivering really a lot of extremely interesting discoveries, in particular about small planets, like the one that I was mentioning before. I mentioned CHEOPS that was launched in December 2019. And is basically CHEOPS is refining some of the sizes of some of the planets discovered from the ground or even by TESS. And later on, the Plato mission to be launched in 2026. The idea of Plato is to really focus on small planets in the habitable zone of solar type stars. So really more focus on this specific type of planets. But also I mentioned many missions that are using the transit techniques to discover new planets. But there are other methods really to discover exosolar planets. And here I'm just showing one of those methods, in particular the direct imaging. What you're seeing here is a beautiful portrait of a planet. The planet is Beta Pictoris b, and this is not an artist's view, it's really a real picture. And so the black spot in the center that you're seeing is the star here and star here. And it's black because in order to see the planet, the star is so bright that in order to see the planet, you need to use some devices to mask out the light from the star. And so here they use a coronagraph in particular to obtain this kind of effect. And so here you can see the planet, the Beta Pictoris b, in 2 points of the orbits. So I think it's quite spectacular to show the potential of this particular method. But additionally to finding new planets, we have a number of new questions that we really want to start to address in the next decade. And among this question we have, why the solar system is as it is. If you compare the planets in our own solar system with all these exotic words I just mentioned about at the beginning, then it is clear that the solar system is not necessarily the standard model of planetary system in our galaxy. And so all of a sudden we start to question why the solar system as it is, why the Earth is as it is. What is the difference between what happened in the formation process of our own solar system compared to other solar systems in our galaxy? And we still don't know in great level of detail. Clearly, we're all interested about the composition of exoplanets, whether they are more gaseous like Jupiter or Saturn in our own solar system, or more rocky like the Earth or Venus and Mars, or potentially anything between, as we suspect it might happen for many of the worlds discovered so far. This seems to be more of a British question. What's the weather like there? But another important question is why are they so diverse? Why we're seeing planets of all sorts of sizes around every type of stars with a lot of exotic orbital configurations. Again, examples that we're not seeing in our own solar system. We believe this diversity must come from formation process and also how they evolve through time. But of course, we need to understand much more. And so clearly we need to have more constraints from observation in the next decade. Clearly, the question of habitability is an important one that appeals both scientists and anybody really. So clearly this is something that also we want to address as much as possible. So what do we know exactly about these exosolar planets that are discovered? I told you that we know more than 4,000 more or less right now. And I would say, unfortunately, for most of those, we don't know very much. For the planets that have been discovered through the transit method, we know the size, so we know how big they are. For most of those planets, we also know the mass, so how much they weigh, using the radial velocity technique. And so if you have the size of these planets and you know the mass, then you can calculate the density. And if you know the density of the planet, then at zero order, you can start to match this density with some models. Sorry, this is a complicated graph. But just to say that all these colorful points are all measurements of planets discovered so far. In this axis, you have the mass of the planet in units of masses of the Earth. And in this axis, you have the radius of the planet in units of Earth radii. And so if you take one of these points, then you see that you have all this line. These are all models that are suggesting what could be the composition of the interior. And so, for instance, if I'm selecting one point here, it could be, when I say 100% H2O, I mean all ices in the interior. Clearly, we're talking about more solid type. And although this seems to be unrealistic, actually, many of the moons in our own solar system around giant planets have a great fraction of ices in their interior. So it is possible to conceive that many of these exosolar planets might also have some ices in the interior. But then we have also some denser objects in this area here that are more similar in terms of density, at least, to our own Earth or Venus. So potentially more rocky type, but maybe also more exotic one. And then up here, we have objects that are not very dense. And so that's where we have more Neptune-type planets, or when the planets are even less dense, potentially even gaseous one. So these are all zero-order sort of classification. And unfortunately, we don't really know whether this is correct and to what degree this is correct. Because, human beings have the density of salty water, but clearly we are much more than salty water. So the density can bring us up to a point. On top of that, we know how distant they are, these planets, from the star. And if we know what type of star they're orbiting, we know the distance, we can estimate the temperature on the planet. But again, it is an estimate, it's not always a direct measurement. But most recently, we have started to find way actually to probe the composition of the atmosphere of these planets and also measure some other characteristics much more directly. And one of the methods that's been very successful in doing that is the transit method. So I have a couple of slides just to explain how this particular method works. So for planets that are transiting, and what you're seeing here is not an exosolar planet transited, is actually Venus, is the transit of Venus that was observed through the satellite Hinode. And so, as you can see here, while Venus is passing in front of the sun, is covering a small fraction of the sun during the transit. And so you have to imagine that for transiting planets, it's exactly the same. So also for transiting planets, we have basically that while the planet is transiting, a fraction of the stellar surface is covered, is masked. And so the light from the star is decreasing a little bit during the transit. The only big difference is that for exosolar planets, the star is not the sun, is not so close to us. The star is very far away, is 10 or even some 100 light years away from us. So it's just a point source. But we still see a decrease in the light of the star while the planet is passing in front of it. And so if we measure how much light the planet is masking, then we can work out basically what is the size of the planet compared to the size of the star. And so this is a great method already for discovering planets. This is the method that has been used, for instance, by Kepler. But then you can do much more, because while the planet is passing in front of the star, while the planet is transiting, if there is a thin atmosphere around the planet, so a thin layer of gas, then we can work out what is the chemical composition of that atmosphere. And the way we do that is basically to decompose the light from the star that is filtered through the atmosphere of the planet. Being made of gas, this atmosphere will be more transparent at some wavelengths, but it will also be more opaque at some other wavelengths. And that depends on which gases are absorbing in the atmosphere. The gases, or if you want, the molecules absorbing in the atmosphere, each molecule has its own unique absorption pattern. And so imagine like a signature. And so when you capture this signature, because you're measuring the light from the star filter through the atmosphere of the planet, and so you will capture something like this. So you will see basically some patterns as a function of wavelengths. Then we can work out of this pattern what are the molecules absorbing there. But we can also work out if there are some clouds, what is the temperature of the atmosphere, and so on and so forth. So we can really extract a lot of information. So I have just a few examples, just to give you some ideas. Clearly, I don't want to spend the entire evening talking about specific examples. But let's just say that so far, the Hubble Space Telescope and the Spitzer Space Telescope were used very successfully for doing the kind of measurement that I just described. And both of these observatories were not really built in the first place for doing these measurements. So I think it's quite incredible almost that we are able to do this measurement with these telescopes. And these measurements are typically very challenging to do for exoplanets because we're talking about precisions between 10 and 100 parts per million compared to the light from the star. So clearly very, very precise. So it means that if your instrument is not good enough, you really need to put a lot of efforts in the post-processing, in analyzing the data to remove basically all the noise coming from the instrument. And so far we have recorded in general about the spectra and therefore some information about the atmosphere of 60 more gaseous planets, so more Jupiter or Neptune-like. And in most of this spectra, we are seeing some indications of water vapor being present. Well, it's not too surprising. First, because for all this hot, Jupiter's water vapor seems to be relatively abundant. Of course, the most abundant gas is hydrogen. They're mainly made of hydrogen. But then there is also a little bit of water vapor always. And water vapor has a very strong signature in the infrared, in particular in the wavelength region that can be probed through Hubble. And so again, it's not too surprising that we are seeing water vapor in many cases. In many cases, we're also seeing clouds and also some other molecules. But again, we are really just starting this because, as I said, these are not necessarily well-equipped telescopes for doing this kind of measurements. Again, also with Hubble, we started to push the measurement to look at smaller planets. In particular, one example is this 55 Cancro E, which is an interesting planet. It's more or less 8 Earth masses. So one of those objects that sometimes we call super Earths. But this is one of those planets orbiting extremely close to the star, with temperature well in excess of 2000 degrees. So it orbits in less than 1 day, so very, very close to a star. And so it was a little bit of a surprise when the Hubble data seemed to indicate that there is possibly a bit of a volatile atmosphere around this particular planet. Again, the measurements are a little bit noisy because we're talking about a relatively small planet, and so Hubble clearly is struggling. But still, I think it's great that we can already start to look at planets that are relatively small in size. Again, if you're interested in habitability, this is not the right one, not because of the composition of the atmosphere, and certainly not because of the temperature. But if you're interested about more habitable zone planets, then I'm sure you've heard of the TRAPPIST-1 system, these 7 planets in between the size of the Earth and Mars that were discovered a couple of years ago or so. And the system is very peculiar because it's very compact, and they're all orbiting around an ultra-cool star. So many of these objects, well, if we estimate temperature of some of these objects, we're more or less in what we call the habitable zone. So clearly, we're very interested about these planets. But so far, the measurement from Hubble haven't really delivered too much information. Again, the kind of signal that we are hoping to extract out of this planet is much smaller than what is the current precision. So again, we need to wait for the next generation of space telescope. Another example that I want to show you is this planet K218b that we analyzed 1 year ago or so. And we discovered the signature water vapor in the atmosphere. And this particular planet is interesting because, again, it's one of these super Earth or ocean planet or small Neptune. We still don't know too much about the nature of this particular object. But the temperature is more or less the one of the Earth. So that's make it an interesting object. And we know that in the atmosphere, there is some water vapor. The signature of water vapor is pretty clear. So we still need to know more about this planet. What are the other chemical species in the atmosphere? But again, I think it's very interesting that we can start to look at example of relatively small planets and relatively cold one as well. I mentioned direct imaging, and you can use direct imaging not only to discover planets, but also to, again, do a little bit of spectroscopy, and also in that case, understand the composition of these exoplanet atmospheres. And so this is, for instance, an example. The spectrum you're seeing here is an example of the kind of spectra that you can observe from the ground for one of these planets discovered through direct imaging. We're talking about large planets like Jupiter or so, but located at very large distance from the star. And this is because this particular technique is more adapt to look at planets at large separation. So looking at the future, I mentioned that the current instrumentation are not ideal, but we are all looking forward for the launch of the James Webb Space Telescope next year. 6.5 meter telescope will be launched in L2. which is this very stable point at 1.5 million kilometers away from the Earth. And the instrument will be extremely sensitive. And so I think James Webb will be absolutely ideal, for instance, to look at the atmosphere of the TRAPPIST-1 planets. The deadline for submission of proposal is at the end of this month, so I'm sure that many scientists will propose this planet as a potential object to be observed by Hubble, but also the K2-18b that I was mentioning before will be a great target for James Webb, and clearly James Webb will have the capability of knowing much more about the nature of that planet, not just finding water vapor like we did in the case of Hubble. But I also want to spend just a few minutes before finishing to talk about a mission that I'm very involved in, which is Ariel. Ariel is a space mission dedicated really to understand the composition of a large number of exosolar planets in our galaxy. We proposed Ariel back in 2015 to the European Space Agency, and then we were selected, and we went through a pretty fierce competition, and then in the end, the three candidates had a final competition, and in 2018 we were selected to be the next medium-sized mission to go forward for the European Space Agency. And we studied Ariel then for some extra couple of years after the selection, and I'm pleased to say that on Friday last week we were finally adopted by ESA. So it means that the mission will fly in 2029. We're talking about a 1-meter telescope that will be launching L2 like James Webb. I will do spectroscopy from the visible down to the infrared simultaneously. The unique selling point of Ariel is to observe about 1,000 exoplanet atmospheres. And we want to include every sort of planets, more rocky, gaseous, different temperature around every sort of stars. And we really want to do spectroscopy, and so really understand the nature, the composition of these planets. And through that, we want to understand how this planet formed and evolved. The payload of Ariel is built by a consortium of 17 ESA countries, but I'm pleased to say that last year a NASA contribution was approved. So we also have the CASE team, and the PI of CASE is Mark Swain at JPL. So what ESA is providing is the spacecraft, is the launch and the operation, but actually the instrumentation all provided by this consortium. I just have a couple of examples of how the spectra of Ariel will look like when Ariel will fly, in the case of a hot gaseous planet, and just in one transit, and piling up a few more transit where we're talking about a small Neptune. So clearly the kind of signal that we'll be able to extract, it will be fantastic compared to what we can do today. So clearly we're all looking forward to this facility. The Ariel team is growing, and at the moment we have the participation of about 200 scientists and engineering coming all from all these 70 countries plus the US. So clearly the Ariel team is increasing, and that's great because there is really quite a lot of work to do. But we also really want to encourage from the beginning strong participation from the open community, not just from the scientists. And in particular, we have a number of colleagues that are working already right now to get the help of amateur astronomers to refine, in particular, the ephemerides of these planets. And this is because since Ariel will focus on planets that are transiting, many of these planets were discovered a few years ago. And if you don't keep checking in a certain sense when the transit is occurring, since for many of these objects we don't know the orbital configuration with great precision, then we might lose the precision, and by the time Ariel is flying, we might have some errors in the time when the transit is occurring. And so that would be not good, because it would clearly decrease the efficiency. We risk to observe the star in a moment when the planet is not transiting, so we really want to avoid that. And since most of the targets that Ariel will include in this catalog are orbiting extremely bright stars, you don't need big telescope in order to follow up this transit and know where that occurs. So even very small facilities from the ground are absolutely great for doing this kind of work. And so the ExoClock initiative in particular is collecting the help of all the amateur astronomers around the world. They have a website, exoclock.space, where they basically, you can include where you are, when you want to do the observations, and you will have a long list of planets that are visible to your area in the world when you want to observe, with the priorities that are needed to do the observation for Ariel. And so we already have really many amateurs that are now helping us in refining the ephemerides. And there are also other projects on top of ExoClock. There are others also in the US that are helping us also to refine in all the stellar and planetary parameters. So clearly this is a big help. But also we have many other initiatives that we're doing. And in particular, last year we had a very successful data challenge where we asked the help of amateur machine learning, but also professional machine learning scientists. And so the challenge was about how we can best correct our data for stellar activity when, in particular, the planet is crossing some spots or some faculae in the star, which is a very well-known problem, but not always so obvious to correct. And so this data challenge was extremely successful. We had the participation of 120 teams from all over the world, and the first 3 winners were awarded during a number of meetings at the European Conference of Machine Learning, but also an Ariel meeting in ESTEC. So it certainly was a great initiative and a great outcome. So we plan to have more of these initiatives, especially now that Ariel is selected, is adopted. And so if you're interested in any of this, have a look at the website or even write me if you have any questions, because clearly we need the help of everybody. I have a couple of more slides, if that's okay with you, before wrapping up, also about another initiatives that we are doing about a small mission, also to characterize exosolar planet. The mission is called Twinkle, and it will be managed by, it is managed by Blue Sky Space, which is a private company that we have founded some years ago with some colleagues of University College London, but now has attracted many private investors. And so the idea is to build a small satellites, repurposing small satellites as they're built for Earth observation. And so we're working in collaboration with Airbus and ABB. And so the idea is to use one of the satellite for Earth observation, repurposed to do spectroscopy of exoplanet or solar system objects, including solar system planets or moons or asteroids. And the idea is basically to build the telescope through some private investment, and then basically scientists or anybody really around the world can pay a subscription and get the data. So it is a new model that for the moment has been exploited more for ground-based telescopes and mainly for cosmology. But we hope that also for exosolar planet, this is something that can fly. And such there are already a number of universities that are interested in this model and have signed some contracts with us. With Twinkle, we have also a number of more educational initiatives, and in particular, there are a number of programs that we are putting in place. One of those orbits is an education program that is linking PhD students from universities. In particular, we had a pilot more at UCL with high school students, especially high schools with pupils that have a disadvantaged background. And so basically in the end, some research papers are being written with the participation and the authorship of some of the students in high school. And this gives these pupils basically the possibility to learn what it means to do research. And if they're interested in going to the university, having some publications really helps their application. So it's quite successful initiatives, and we hope to be able to grow in the future. Okay, so I believe my time is over, so let me wrap up the conclusions here. Exoplanets appear to be ubiquitous in our galaxy, so that's something we learned in the past 20 years or so, in particular thanks to Kepler. And while the number of discovered exoplanets is increasing exponentially, we still know very little about them. And so this is something that we clearly want to address in the next decade. For sure, we have already a suite of dedicated space missions, but also ground-based telescope in the next decade to discover more and also more interesting planets. And I mentioned TESS, Cheops, and Plato from space, but there are many facilities also from the ground. But when it comes to really understand more the atmospheric composition and structure, then clearly James Webb will be a fantastic observatory. Unfortunately, perhaps a little bit too oversubscribed because many scientists working in astrophysics will want to use James Webb for all sorts of reasons and all sorts of great ideas. But hopefully in part will be used also for exoplanet. I mentioned Twinkle, there's these initiatives for this small satellite to be launched, if all goes well, 2023 or 24. An Ariel that will become a reality in 2029. An Ariel will really have the idea to be dedicated completely to the study of the atmospheric composition, and so really go for the big picture because we're going for the large statistics, the large number of planets to be looked at. And so my last message is this is absolutely great to have all these exosolar planets discovered, but unfortunately we can't really go there. They're still too far away, even the closest one. And so I think it's always good to remind ourselves that we need to take care of this one first, because we don't have for the moment a plan B. So thanks so much for your attention, and I'm more than happy to answer questions if you have any.
A question about the design of the spacecraft. There's that cylindrical part, and then underneath it are like flaps or wings. They look a little bit like what's the heat shield for James Webb, is that heat shield for your spacecraft?
So you're talking about Ariel? Is this the
Yes,
figure you
Ariel.
were? Yeah.
Yeah.
So actually, it's very similar. Well, it's much smaller than James Webb. So James Webb is 6.5 meter telescope. Ariel will have a 1 meter class telescope. So we're talking about a much smaller and lighter satellite to start with. It looks a little bit more like Planck. I don't know if you
Okay.
if you have
Yeah.
seen that.
Yeah.
So basically here you have V grooves, and the idea is to use them to passively cool the instrument. And this is because we want to passively cool most of the telescope, and we will actively cool, on the contrary, the infrared detectors. But basically, each of these V grooves is irradiated, and so is irradiating, and so is basically keeping an increasingly cold temperature towards the instrumentation.
Okay, so it's more of a radiator than a heat shield.
Yes.
So James Webb's going to be far out in space at a Lagrange point. Will this be in orbit around the Earth, Ariel?
No, Ariel is also in Lagrange point L2,
Okay.
so it's the same orbit of James Webb.
Okay.
We will have a slightly a larger angle of for the observation, simply because because of how it's set up. In the case of James Webb, they need to be even more careful not to have any contamination from the sun, because clearly they want to look at first galaxies, so it's extremely sensitive, and it goes also much longer wavelengths. But that is the only real difference in terms of sky visibility. It's quite similar.
Okay. Well, thank you.
Giovanna, this is Bruce. A question: is it presumed that Ariel will have the kind of resolution and spectroscopically that you could maybe detect small organics in exoplanet atmospheres, or is that not possible?
Look, it's a very good question. Ariel is more calibrated in a certain sense for warm and hot planets. And this is because we know we have a very long list already of existing planets with those characteristics, and also because in terms of big picture for the chemistry is very valuable to look at relatively hot planets for several reasons. One reason is, if you look at a hot planet, then through the atmosphere you also get some sense about what is the composition of the interior, because for hot planets the interior and the atmosphere are much more in connection. The colder is the planet, the more the chemical species somehow are subtracted out of the atmosphere and are embedded in the interior. But for probably a limited number of planets, especially the ones that are orbiting very bright stars, we can push towards a colder temperature. Said that, it will not be the sweet spot of Ariel. And so I think for those planets that you're referring to, I think James Webb is the best bet, because it's big and because it's very sensitive. So you really want that when you want to go to cold objects.
Thank you.
Giovanna, John Hepler, I have a quick question. What's the lifespan expected for Ariel?
Well, for the moment, the lifetime is 4 years. That can be extended to 6, but in reality, there is nothing really that prevents the mission to keep going, and we clearly hope it will be the case if we don't have any issue with the instrument. So the 4 year comes from costs. His operation are great, but they're costing 10 million per year. So if you need to stay in a budget, then you need to be very careful also with time.
Okay, thank you.
I have a question on Ariel. Does it only measure the spectroscopy of planets that transit, or would it be only, or ones that orbit but are not in the plane that we would see? In other words, face on versus edge on.
That's a very good question. In principle, you can also look at those planets that are not transiting. The issue you have there is that you don't know the radius of the planet to start with. So you have much less information, you have more degeneracy. It was done in the past, in particular, looking at some phase curves with the Spitzer Space Telescope. And so you can still capture all this variation throughout the orbit. And I think that we might have a few targets of that type. But the fact that you don't know the radius, you don't know hover information like you have when the planet is transiting, makes this planetary candidates perhaps less optimal. So it means that it needs to compensate with something else that is really interesting.
Thank you.
Dave Hockenberry here. Just a perspective question. We in the United States are used to having budgeting problems and getting these missions the appropriate money that they need, not only for development, but also to get them off the ground, is always like herding cats. Does the European Space Agency have many of these problems as well, or is it just unique to the United States?
I think all the agencies in the world have the same problem. So I think, having 17 is a country. Well, in part it's because it's great to be able to have a large team and to do things in collaboration, but it also, prevents disaster if any other country pulls out, and it has happened in the past for many missions, and we should expect this sort of crisis to happen. In general, they do. And so, if you are a big consortium, then you always have the chance somehow to have somebody else that can pick up. Even since 2015, when we proposed, there were many of these crises, and then they were solved. And launching this type of missions, it is expensive, and it's expensive for every country in the world right now. And so that is why I think it's particularly important to collaborate among many countries. I personally think that is also very enriching. So I think it's in any case a plus, but certainly doing things together really prevent that some of this disaster might happen. Disaster meaning, big partner is pulling out, and then all of a sudden you have a big problem you can't solve.
Thank you.
This is Bruce again. I wonder, since we have you as kind of on the line here, if you could comment on your thoughts about the publication a month or two ago in Nature Astronomy detecting phosphine gas in the upper cloud decks of Venus. Your thoughts on that? Maybe just seems to fit in your wheelhouse in terms of specialty. And I'm just wondering comments, critiques of some of those findings.
Well, it is an interesting question. And certainly that article was very thought-provoking. It certainly provokes a lot of discussion and debates. And I think it's always important in science to have this debate. I've seen that there were some papers after that where some of our colleagues looked at the ALMA data and then took a slightly different view. And so I think it's fair to say that perhaps this discovery is a bit more controversial at the moment. I think in general, independently on this particular paper, when it comes to talking about life in the universe and detecting biosignatures, I think we all need to be very careful. Simply because it's so easy, perhaps, to interpret in a geocentric way, I should say, something that perhaps in a different environment might be due to something different. And in fact, I am one of the people also that when I was younger and was in the US, I was very interested in astrobiology. I'm still interested in astrobiology, don't get me wrong, but I was perhaps sure that, you know, we will see a planet at a certain point, we will look at the chemistry and it will be obvious if there is a biosignature, because look at the Earth compared to all the other planets and so on and so forth. And then with age, I became more cautious simply because seeing at the variety of chemistry that we're seeing, even among the simple objects, which are this big hot Jupiters, I think we are far from understanding completely what's going on. And in part it's because of, for sure, the observation are not ideal, are not optimal. There's still a lot that we need to learn, but it don't seem to be so simple and so obvious. So I'm starting to question whether we'll be able straight away to understand when we see a biosignature, if and when we see one. And so I think Ariel, in a certain sense, was also put together with the idea that we need to have a big picture first, a big picture of planets that are for sure not habitable. To understand all this exotic environment, all this chemistry that we're not used to, for which presumably we'll need to have years of lab work to reproduce some of this reaction, understand why they are, what kind of chemistry we are looking at. And I think that would be very important and necessarily to understand better when you move towards colder environment like the one of the habitable planets, that almost by definition are more complex environment to look at. So because the colder you are, the more complex becomes the chemistry. And so these are some just words of caution, because I think there is quite a lot that we still don't understand.
Thank you. That's great. So really, really balanced answer. So thank you.
I don't see solar panels. So is it radioactive isotope power?
Well, there is a little bit of solar panel, but they're not huge.
So what is powering the spacecraft?
Well, a little bit of the solar panel that, although they're not huge, there's still a little bit. They're not visible in this particular view of the spacecraft. If you go on the aerial vision.space, then you will have a nice movie that is showing a little bit how the spacecraft is moving. And
Yeah, thanks.
And there are also many publications that you can also look at in the aerial vision.space, some also more technical. So if you have any specific question or curiosity, then if you don't find what you're looking for, drop me a line. I'm happy to point at the right publication. I should also mention that very soon we will have a website that will make public all the planet candidates that are considered by Ariel. And of course, the final list will include about 1,000, but we have many more candidates to consider. And so that website will update the entire community about what are the candidates, and we will encourage some feedback from anybody, because on top of the planetary and stellar characteristics, we want to make sure that in the final decision, we will also keep into consideration any information we have about the system.
I have another
So this
question.
is Roger Taylor, and I had a question that we were talking about launching in 2029. When we look at how exponential the discovery of the exoplanets are. By the time 2029 comes along, you might have tens of thousands of candidates. Do you have a methodology for which ones you'll look for and which ones you'll not?
That's an excellent question. So we certainly are expecting that sort of numbers. And in fact, when we presented the science case for the adoption, we had the two versions. Ariel, if it were launched tomorrow with the existing planets, what we already know, and the projection into 2029, and knowing what are the expectations from tests in particular, and also other facilities. So we want to make sure that we are covering well the parameter space of the planet and the star in terms of sizes, of temperature, type of stars. So in a certain sense, we want to make sure that we have in each point in this parameter space at least a few examples of planets, and which one in the end we will select in part is also through this website that will collect all this information, but also the input from anybody in the community that will be able even to vote or to provide some input on why we should go for one instead of the other. Once this list of more than 1,000 more or less will be selected, then the idea is for many of them we will not know anything. Some perhaps will be already known to a degree because there will be already some observations, in particular from James Webb, but also Hubble. But for many, we don't know anything really. And so what we're thinking of doing is a sort of 3 tiers observation strategy. We go for the tier 1, which is a sort of shallow survey of the 1,000, a relatively low resolution. And then out of those, we select half of them to go for a deep characterization. And so we use the tier 1 sort of shallow survey to inform what are the best targets, then to continue to observe for the tier 2 and so on and so forth, to avoid to waste some of the time on targets that perhaps are all overcast and so for some reasons are not particularly interesting.
Is transiting observations the only way that exoplanets can be discovered, or is there another method with measuring the wobble of a star that can be used?
Yes, for sure. Radio velocity, so the wobble of the star, it's certainly another excellent method to discover new planets. If we want to focus with Ariel on transiting one, then out of the planets that have been discovered through radio velocity, you need to check whether they're transiting or not. And this, to a degree, is something that CCAS is doing. CCAS is certainly focusing also on radio velocity planets and checking whether some of these planets are transiting or not. But also Gaia. Gaia so far hasn't yet delivered exoplanet through astrometry, simply because they are not yet in the final release of the data with the precision that will be needed. But that will happen very soon. And also out of Gaia, we expect that we will have some interesting targets to add to the collection.
Thank you.
Any other questions or comments for Giovanna?
That was excellent. Thank you so much.
Yes, thanks so
I
much,
have
Giovanna.
one quick question.
Oh, sorry.
All right. So I teach first-year students at a small college, and this semester we are reading Edgar Rice Burroughs and Ray Bradbury. And knowing from scientists such as Carl Sagan about how influential science fiction has been for their development and in gaining an interest in astronomy and physics and the physical sciences, I'm curious, what was your inspiration?
Sorry, what?
What was your inspiration?
Okay. Well, I grew up with, I don't know if that was the inspiration, but I grew up with some Japanese cartoon that was all about very evil sort of aliens that wanted to invade the earth. So I don't know if that was something that just grew in my mind. But perhaps more interestingly, when I was doing elementary school, I had a math teacher that she was very inspiring, and she encouraged me to read some relatively simple public science book about physics. And I found that extremely fascinating, and I was completely hooked. So yeah, I think all this can help, and sending a message to young students that science is interesting, and they should seriously consider doing that if they have that interest. It's very important. I don't know what the situation in the US, but I was quite shocked and appalled to hear that in many cases in the UK, some girls at school they drop science because somehow they think they are not good enough for doing science, and so clearly any message that can reach them to encourage them not to listen to this sort of hurdles.
Fortunately, we have the same situation here, where it seems like girls are programmed to expect not to be good in math and sciences, and boys are. And it's definitely societal programming, and it's not good at all. So, can you recall the name of the Japanese cartoon? Because two of my students are from Japan. I want to question.
I do. Now, the name I have, I know this because I've been discussing this with some Japanese colleagues. So the name I have, of course, was a name that was translated somehow in Italian. So it's perhaps not really the Japanese name. And my colleagues told me that actually those cartoons were relatively old when they arrived in Italy. And so in Italy, they were called Goldrake, Jigsaw, but then they understand that might not be the original name.
Okay, I'll see if I can find it.
But they were, I mean, I can certainly send you a link so you can see what the cartoon is.
Yeah.
And
that would be great.
at least for me, they sort of inspire me more to go into astrophysics.
Okay, thank you. Thank you.
Well, again, thank you so much, Giovanna, for taking the time, and especially with the late hour we have now. We really, really appreciate your talk. It was wonderful, and thank you for entertaining the questions as well.
Thank you so much, really. That was my pleasure to meet you all.
Yes, we wish you the very best with all your work as well.
Thanks so much.
Take care.
Great to meet you.
Bye.
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 Thank you.
Thank you.
Bye.
Thanks so much.
We're back. Oh.
Hey. Okay, here we are. Wow.
That was a great talk.
Yeah, she was good. Really
It
good.
was.
Hi. Hey, Kathy.
Hey, Kathy, hi.
Nice to see you.
Yeah, it's warm down here in Florida.
Yeah, rub it in.
You're in Florida?
Yeah, it was about 75 today and sunny and beautiful. And
Oh man, you suck.
Okay.
You suck.
Yeah.
Thanks. I know.
No, it's beautiful here. Nice and crisp, clean fall day. We can look at it that way, right?
Right.
I'm wearing t-shirts and shorts. How about you?
And a turtleneck. Okay.
Shirts and heavy socks. Yeah.
Yeah, a parka. Yeah.
Yeah, I was out last night observing it. It was cold.
I was tempted to get up at 4 for the Leonids, but I didn't do it. It was cloudy when I looked out, so.
No, it was clear when I was out there.
Did you see any Leonis?
See a limit, Leonid, meteors?
Orion over here.
No, I didn't really stop to notice that. I was just mostly concentrating on all the open star clusters up in Cassiopeia.
Okay, around 4 a.m. it looked cloudy. That's when I would have gotten up.
Okay.
So it cleared up at some point.
Well, Bruce, you're going to have a hard time topping that one.
Yeah.
Yeah, okay.
That was a good one.
Challenge has been laid. Okay, I get it. Anyway, no, I'm glad it worked out. And, thanks everyone for accommodating the time difference too. I mean, I know it's much earlier, so thank you.
Did we
no
have
problem.
it? Did we have a meeting before she spoke? Like, did
No, we did not.
because I was late. I came in late.
Get her right.
I didn't know, I had mentioned this before. I didn't know if Don, if you wanted to do the night sky for this month. I mean, this is our last quote official meeting of the year. It's up to you.
I can't even, I mean, not everyone's hungry, ready to get to dinner. I don't know.
No, go.
I have a question before we do anything else. So traditionally in December, we would have a holiday get together.
Right.
Are we going to be doing that via Zoom like we did over the summer with our?
I think it's a great idea.
Yeah, we talked about doing that. We talked about doing that, yeah.
Yeah, when would be a good time?
I'll need the date so I can update.
How about the regular Tuesday meeting time?
That'd be
Well,
fine.
is Kathy buying the drinks?
I'll send them all to you.
You have witnesses, Dave. She said she was, okay?
So then the regular date would, the
The
regular
second
time and
Tuesday?
everything would be the 8th.
Yeah, the second Tuesday, that would be fine. Sure. Why don't we do a Zoom get together?
He has to do delivery.
That might be a problem.
Uber Eats for 50.
Have somebody else do delivery.
Yeah, that'd be fun.
Clock?
Set that up.
7?
Yeah, 7 o'clock, the usual time
Yeah.
Okay.
on the second
It was
Tuesday.
December 8th.
All right, everybody wear their festive colors.
Well, and we topped out around 48 or 49 attendees tonight we had.
How many were on YouTube?
Yeah.
We had about 17 on YouTube, and I think I maxed out at 27 on Zoom.
Wow.
It was good. That was well
That's
attended.
great.
I think the hour, discouraged a few people, but we
Good
had-
subject matter.
My cats are very unhappy because they are not getting dinner right now.
That's my dog. I'm trying to feed her while we're talking.
Well, I had to turn off.
He was
Yeah,
really good.
yeah, I had to turn off
That was
I
great
had to mute
talk.
myself and everything because they were like. Anyway, I hinted earlier about some changes, and so I am losing my job at the end of the semester.
No.
And I am putting the house on the market beginning of December,
Oh, my.
and I have decided to come back to Pennsylvania.
That's good.
So,
We welcome you.
Where in Pennsylvania, John? You going back with your parents?
well, it looks like, well, my father has made it very clear that my 4 cats are welcome to come home. I can come too. But cats,
You
the
feel the
cats
love?
are number one. I can, I'm okay, but the cats can come home. So I might end up in, ironically enough, probably just as far away, but in Schuylkill County. So we'll see. I'm not sure yet what's going to happen, but it really comes down to how quickly I can sell the house.
Mhm.
And I will be able to keep my part-time job at night teaching online with the
Oh,
community
good.
college. And I can do that. I can do that from anywhere.
Yeah.
So,
Oh, good.
so-
Sorry to hear that, John, but hopefully
Yeah.
things will.
Yeah.
Well, you know what? To be honest with everyone, it's been really, really bad down here for the last probably year and a half in terms of the college's situation.
Mm.
And I had pretty much decided this was going to be my last year anyway. It's always nicer when you decide to leave rather than when they tell you you're leaving.
That's the best way.
So it happened a semester early, but I had pretty much decided that this was going to be it. When they cut the retirement match, I was thinking like, okay, time to start thinking about something else. So,
Yeah, yeah.
anyway, and so logistically might be affected with any type of relocation in terms of connectivity to be able to update the website or produce newsletters. So bear with me.
Just keep us posted, John. And
Okay.
we're behind you 100%, whatever you got to do.
If you need help, just say the word, I have Publisher on my computer. I can work on it.
Oh, I thought you were offering to like help me move.
Oh, that's true. That I don't have a pickup truck anymore, but we can do that. Sure.
You know, my roommates, the 4 cats, my roommates they're just like no help whatsoever. Just lay around and look at me.
Are you
climb in
trying
the
to,
box or things like that?
are you trying to say that Rock Hall doesn't have a big staying power to it?
I really love this little town, and I'm going to be sorry about leaving that. Yeah.
Well, it's certainly changed since I grew up around there.
It's yeah, and unfortunately this year has been really tough on the town too.
If you rent a big truck and need help loading up, let us know.
Yeah, let us know. Seriously.
We'll be there.
Kathy will bring the drinks.
Socially distanced movers.
Drinks.
Yeah, Kathy's buying. She bring the beer.
I'll bring the beer. Bring some white wine for you, John.
There's a couple good pizza places in the area, so we could do beer and pizza. So
Beer and pizza.
that's
right.
what you need for moving. Anyway, all right, enough about me.
All right. Well, Don, if you're up for a quick "What's up in the night sky," well, I think we should do that after the evening so we can eat.
We'll do a quick one. Let me fire up Stellarium here and then do a screen share. Where's Stellarium? There it is. Did anyone see any Leonids last night?
Nope.
Cloudy here. I couldn't see the launch on Sunday night either. It was cloudy.
Poor Kathy.
Bummer.
I went out at 5:30. How do you suffer? It's too cloudy.
All right.
Look like you're in the transporter in Star Trek, sweetie.
You do.
Okay. Are we seeing Stellarium?
Yes, we are.
Yeah.
Okay, let me get things organized a little bit. So as I usually do, I'm going to keep my menus open. I'm going to turn on the constellations. And I like to take a quick look at these, but I don't leave them up for long. But they're fun to look at. So this is real time. This is like what's out there right now. So it must be the new moon must be setting, huh?
Yes.
I didn't even know that. I haven't been keeping track of that thing, but I bet it's a beautiful thin crescent out there right now. So wow. So that means the next couple nights could be clear and cold. Should be beautiful for moon gazing. And I guess as a day or two go on, we're going to have a very nice semi-conjunction here. And speaking of
Out the
conjunction,
window. There it is.
the closest conjunction in centuries is going to happen right around Christmas with these two. They're going to be in an eyepiece. You'll see both planets at one time in December.
I don't think I've ever remembered doing that.
Now, I think it's around the 21st or something like that, but it will have both of them in one eyepiece. It'll be spectacular.
So it'll be like the Christmas star, right, Don?
See that? See that? So Mars is still looking beautiful. It's fading a bit, but it's still a great time to look at Mars. Of course, probably the highlight of the deep sky right now is our friend Andromeda. It's an amazing, amazing galaxy. Center of that. Zoom on in. And it looks just like that in my telescope. I don't know about yours.
Especially those background stars, right?
Yeah.
Yeah, it's because you have a Questar.
Now,
Can't miss that. Let's see, I didn't turn on my deep sky. Let me do that. Let me turn on my deep sky objects. There we go. These are the guys we want to see.
Nice.
And our favorite in the whole night sky, just about, next to the Pleiades. There we go. There we go. There's the ET cluster.
Oh, yes.
There's his eyes, there's his feet, there's his arms looking, waving at us. the ET cluster.
Let's see that.
It's a great time of year when we have things like the double cluster here, easily visible way over the horizon. Since it's so chilly out, just take binoculars and go out and look about halfway up between Cassiopeia and the horizon, and you'll see this thing. It'll stand right out in binoculars. One of my favorite stars of beautiful color is this one, which is the Garnet Star, named by Herschel, and it really does look red. A lot of colored stars, you don't see the color, but this one you will see red.
Your stellarium's not moving.
Yeah, we can't see what you're pointing at though.
Yeah.
It must be lagging.
Like by a lot.
Wow. Let me
On NG 457.
yeah, that's where I was. Let me jump out.
Here
Share. Should I try it again, or should we have dinner?
Let's have dinner.
I think it's time for dinner.
The president has spoken.
We got a little something there. So
We got a little something at least. But
My dog says.
Thank you, Don.
lagging, so.
Thank you.
So good to see everybody.
Yes.
Yes, it is.
Bye.
Stay safe.
See
Who's
you in
that,
December. Bye.
Help
Bye.
COVID fatigue to see everybody.
Have a nice Thanksgiving, everyone.
Yes.
Yes,
Well,
you too.
have a-
everyone.
Bye.
Bye.
Where's
Have a
John?
safe
Who is-
Thanksgiving.
See you.
Kathy, are you
Yeah,
talking
what
to
do
me?
you-
Roger.
Yeah.
Everybody.
This is Crystal Carrington.
Oh, that's Crystal.
Nice.
Ah,
So glamorous.
there were no cats here with us.
She's my beauty queen. My beauty queen. Yeah. My nephew came down the other weekend to help me start packing, and I almost lost a cat.
Took her home, almost took her home, huh?
Yeah. Oh, yeah.
What a beauty.
What a spoiled cat.
So sweet.
Expensive cat. She's on 2 medications a day. So.
Oh, wow.
Oh, boy.
I'm sorry, we have one on 4 medications a day, so.
Well, no, yeah, I got to count the other ones too. She's just on 2.